Hi everyone, welcome to part 3 of my alarm clock series. I'm jumping ahead of myself a little bit here, and I've decided to design a couple of printed circuit boards for this project. So the first circuit board is going to contain the controller chip, the ATmega 328P, as well as other things such as the LED displays, the buzzer, and some power supply circuits. In fact, the first PCB will contain everything apart from the buttons. The reason I decided to go with two PCBs is because I wanted the buttons to be on the top of the alarm clock and I wanted the LED displays to be on the front. Because they were in different orientations, I figured it's just easier to go with two separate circuit boards. There'll be very minimal wiring between the two, so it won't really be a problem. So let's start by taking a look at the schematic for the main board. So this is the schematic. You can see it's not that complicated. We've got it split up into sections. We've got the controller, the display, some power supply circuits, buzzer, and an input header. So let's look at this one part at a time. Let's start with the power supply. So over on the left here, I've got some screw terminals, which is going to be our power supply input. There's going to be a 9-volt connection there and ground. The 9-volt line will come through this diode. Now the diode gives us some reverse polarity protection. So if the polarity of the power supply is connected the wrong way round, this diode will stop the current from flowing in the wrong direction, hopefully stop it from doing any damage. So that's the sole purpose of the diode. I've decided to go with the LM7805 linear voltage regulator. Now I believe that's not what I said in part 1. I said in part 1 I was going to be using a smaller linear voltage regulator. There's no reason for this. I just simply forgot about that and just went with the 7805 just because I've got some. So I'm going with that. That should be more than adequate for what we need. Now, according to the data sheet of the 7805, we should fit a 330 nanofarad capacitor on the input if our power supply is some distance away from the regulator. And as we will have like a power supply lead on this alarm clock, then yes, there is some distance between them. So I've gone with the 330 nanofarad capacitor on the input as per the data sheet. The data sheet also recommends a 100 nanofarad capacitor on the output, so again that's why that's there. And then I've decided to also fit an electrolytic capacitor, 10 microfarads. I don't really know whether that is required or not, whether it provides any benefit, but my theory is it will act as a bit of a reservoir capacitor. So if the circuit suddenly demands a bit more current, this capacitor will be able to supply that without dipping the voltage. And also having a slightly higher value capacitor and a lower value capacitor should help to filter out any kind of interference that we might have, and they'll work together filtering out different frequencies. So I think it's good just to have some variations between the values of the capacitors to help filter out different frequencies. I've decided to fit an LED. It's like a power LED, so we know when the power is on. Really didn't need to do that because this PCB is going to be enclosed inside a case and we're not going to see this power LED. I'm not going to bring this out into the case. It doesn't really make any sense because the alarm clock has a digital display, so we know when the power is on. So we really don't need this. I just added it for a bit of fun. It'll help me when I'm sort of working on the bench. If there's any problems, I'll at least know that we've got power to the board. I've just gone with an arbitrary 470 ohm current limiting resistor. I think that might be slightly high for a green LED, but I'll try it, and if it's too high, we can always lower it. It's no big deal. So that's our power supply circuit, and that ultimately gives us our 5 volts that will feed around the rest of the design. So if we go up to the controller, This is also fairly straightforward. We've got the ATmega 328P. All of these connections down here are just inputs and outputs. They're all labelled up. What they are doesn't really matter right now where they're going. We've got a power supply here, the 5 volts that we just spoke about coming in here. And I fitted another 100 nanofarad capacitor that will be positioned as close as possible to the VCC pin of the 328P. And then we just got our ground connections here. Now I've tied the analog voltage power supply to the main power supply. Not really using it. I was just uncertain whether or not it's a good idea to leave it floating or open, so I've tied it to the main one. And the analog reference voltage I've just left that not connected. I believe that's okay. Up here we've got the RX and TX, again no connections here. These little green crosses, by the way, indicate a no connect. That just tells the Easy EDA software that we've deliberately not connected these pins. So when it does its checks to make sure if we've missed anything, it'll know that these are not required and they can just be ignored. And there's the one down there as well. Other than that, we're using every single pin. Over here, I've got my 16 megahertz crystal to provide a clock. Now, I believe you can run the 328P without that. I think it has its own internal oscillator, but it's pretty standard to use a 16 megahertz crystal. We could have used a slower one. This is not a highly demanding program that we're going to be running on with this. And we could have just adjusted our timings to compensate for a slower clock, but I figured it's just easier to go with the standard 16 megahertz because that's what's on the Uno that we did the prototyping on. So we know that if it works correctly on the Uno at 16 megahertz, it should work correctly here at 16 megahertz. So just try to keep my life a little bit easier by keeping things standard. This circuit here, incidentally, is just an exact copy of what is on the Uno schematic. So I believe these are known as load capacitors, and I've just gone with 22 picofarads rather than trying to do any calculations myself. I've just copied what the Uno is using. I figured that should be roughly about right. And I believe the Uno also has this 1 mega ohm. I believe it's called a bootstrap resistor. Somebody correct me if I'm wrong there. I believe it's to help get the circuit oscillating, just to sort of start things going. Again, you probably could leave it out, but I've figured that if they've got it on the Uno schematic, I probably should fit it here as well. So really, we've just got our clock circuit that's connected to XTAL 1 and XTAL 2, which is pins 9 and 10. We've just got the power supply and ground, and then some inputs and outputs, and that's really all there is to the controller. We go across to the LED displays. This is probably where the most interesting things are happening, though it's not that involved. So we've got these 2-digit modules, which I believe I mentioned in the part 1. So I've got 2 of those to give me 4 digits in total, and I explained before the reason I wanted to do that, because I want to spread them slightly further apart rather than pushing them hard up against each other. And then in between the 2, we're going to have 2 little dots that you normally see on a digital clock. And I'm just going to utilize some 2mm LEDs that we got here. They'll actually be positioned sort of one higher up and one lower down, but this is just a schematic showing the electrical connections. The positioning is not relevant. Again, I've gone with some arbitrary 470 ohm resistors for current limiting. I may have to tweak those values. I'll have to do a bit of experimenting, but they should be a good starting point. I really wanted 1mm LEDs, but I couldn't find anyone that sold a 1mm LED, so I've gone with 2mm. I've got a backup plan for that. If it doesn't look right, I might 3D print a black plate that has 1mm holes in it, and then we'll just position the LED behind the holes, and they'll just shine through the 1mm hole. The reason I wanted 1mm is because it's the same thickness as the bars on the 7-segment displays. Now, I'm not sure if these are common anode or common cathode. I will check that. But the part numbers are here, are the correct part numbers that I'm going to be using. So we connect 7 of our signals from the ATmega328. We put them through some current limiting resistors. Again, may have to tweak the values. I've gone with 330 ohms here. I'm thinking because of the multiplexing, we might even be able to get rid of them completely, or we could use lower values to make the displays a bit brighter. I thought in the demo, I think I was using 470 ohm resistors, and I thought in the demo the displays were not quite at their full brightness. I think because of the multiplexing, you're effectively kind of pulse width modulating the signals. They're not on all the time, and it makes them dim. So I think we can lower the values of the resistors to bring them back to a more full brightness. But I'll just go with 330 ohm as the starting point. Now these 7 lines connect to all 4 digits, so you can just see that they're sort of paralleled off across all 4 digits. So they connect to the A, B, C, D, E, F, and G. We're not using the decimal points, so we've got some no connects here on the decimal points. And then on the other side, returning back to the controller chip, we've got four signals here. I believe, God, I've got to get my head around whether these common anode, common cathode, which way the current's flowing. I believe we drive these low when we want to activate the digits, if my logic is correct. So it's fairly simple. There's sort of 7 lines coming in and 4 lines coming out. The 7 lines coming in control the actual number that we're displaying, and then the 4 lines here control which digit that number will be displayed on. And as I explained in the first episode, we multiplex these signals so that we can control all 4 digits. And then just a last couple of little bits. We've got the buzzer. This is going to be the actual alarm. It's going to make the noise. We just need a single connection for that. We'll use pulse width modulation to control the tone or the note that comes out of the buzzer, and then obviously we need a ground connection. And then finally I've got this input header here. It's an 8-pin header. I could have got away with less pins, but I've just allowed for 2 ground connections. We only really need 1. And I've just brought out every pin available on the ATmega328 with the exception of the serial connections, the RX and TX. I haven't brought them out, but I brought all the other pins out. We only need, in my design, we need 5 buttons, so we'll need 5 of these connections. So I've got 6 here. So one of them is spare and one of the grounds is spare. So I could have got away with a 6-pin header, I guess, but I figured I'll just try and give myself a little bit more flexibility, just in case I wanted to do something different, if I want to make any modifications. It gives me some options, although I doubt very much I will be doing anything. So that's the schematic. It's fairly simple. Let's have a look at the PCB. So this is how I've laid it out. I've tried to keep all the power supply circuits over on one side here. So we've got the screw terminals, the diode, the input capacitor, the output capacitor, and then the regulator itself, and then my little reservoir capacitor there as well. So the power comes in on the 9-volt line here, goes through the diode, over to the input capacitor, to the input of the regulator, and then from the output of the regulator it goes over to the output capacitor, and then to the reservoir capacitor. It eventually feeds up to this line here that I'm highlighting, and you can see it goes around various areas of the board. It doesn't have to go to too many places. It goes to a few resistors, and then it's also finally going over to this other 100 nanofarad capacitor, which I've tried to position as close as I can to the power supply inputs on the ATmega 328. I mean, I could have got it a little closer, but I was a bit pushed for space here, so I've sort of moved it over a little bit. I've kept all of the clock circuits together here, so we've got the load capacitors, the crystal, and the bootstrap resistor, and they're going back to a couple of pins on the ATmega. You can see one there and one there. Ideally, the clock circuits, I think, should have been positioned a bit closer. I don't think this is an ideal layout, but I was trying to kind of fit it into this space, and I think it'll be fine. I think it'll be fine laid out like this. We have got a couple of other bits. We've got the buzzer over here on the left. It just, as I was laying things out, that was just kind of an available space. That is some distance away from the controller. I think it's connected on that line there, but it's not too far away. It shouldn't be too bad, and that's really not a problem anyway, distance. And finally, there's the power LED, and then finally we've got this 8-pin header here. It's in the other orientation to how we saw it on the diagram. The ground connections are at the top. So I've thought about that a bit more. I probably would have spun that around. So I like the ground connections to be near the edge of the board. It's just a convention that I try and stick to, and I've broken my convention here. But it really doesn't matter. I've tried to do all the routing on this top layer. The red is the top layer, and you see all of these lines here generally running horizontally across the circuit board on the top layer. Now if we have a look at the bottom layer, you'll see the opposite. On the bottom layer, which is shown in blue, all the lines are generally running vertically. I do that for a couple of reasons. One, it means if there's any lines crossing over on the top and bottom layers, they actually cross over at a 90-degree angle, so they should have the minimal amount of interference. But it also, keeping everything orientated the same way on each layer helps the ground plane, which is the solid blue area or the solid red area. It helps it to sort of flood fill throughout the entire board. There are a couple of areas where it didn't reach, for these sort of black areas, but again, really don't think that's going to be a problem. Whilst we're talking about layout, the last thing I want to mention is I decided that rather than going with my normal convention of putting one fixing hole in each corner, I would just lay out the board and then decide, and then sort of look at what available space is there for fixing holes. So they were my lowest priority. It's a fairly small board. As long as we've got a few fixings on it, it's not really going to flex or anything like that. So I just arbitrarily stuck down 3 fixings where there happens to be space on the board. Turns out that was a mistake. In the next episode, we'll look at the 3D printed case design that I've come up with, and I really wish I'd positioned these fixings in a little bit different positions, but we'll see that in the next video. So that gives us circuit board's going to look something like that after it's been manufactured. That's the 2D photo view. And then EasyEDA gives us a nice 3D view of the board as well, which we can spin around to have a look around it. It's a good opportunity for me to show you that the LED displays are on the other side. So we've got these 7-segment modules here. We'll have the 2 additional LEDs in here. That's the only thing that EasyEDA didn't model in the 3D design. Every other component had a 3D model. Just those 2 that are missing, but hopefully that gives you a fair idea of what the main circuit board is going to look like. So this contains everything apart from our buttons, which all connect in via this header here. And then if we have a look at the second PCB, this is the schematic for it. It's very simple because all we've got here is 5 buttons. So I've got one for the time, one for the alarm, one for the hour, and one for the minutes. So the way that will work is you can hold down the time button and press the hour button to advance the hours and the minute button to advance the minutes. So that's how we'll set the time. And then the same will work for the alarm to set the alarm time, we'll just hold down the alarm button and use the hours and minutes to set the alarm time. And then just one last button. I figured when the alarm goes off, I thought that you could probably just press any button to cancel the alarm, so I could still get away with my 4-button design. But then I thought, do we want a snooze feature? Most alarm clocks have a snooze feature. I'm not really going to be using this alarm clock as a real alarm clock to wake me up from sleeping. Probably actually just going to have this sitting in my garage. It's just giving me a digital clock, so I probably won't really use the alarm feature. But I thought, as it is an alarm clock, I think it makes sense to have a snooze feature. It gives us something a little bit more interesting to look at when we come to the programming. So I've put a snooze button on there. I'll talk a little bit more about that when we look at the 3D printed case. But essentially we've just got 5 buttons. We have the same header here that we had on the other board, only this time I've actually labelled up what each pin is, just to help me out a little bit when I'm working out what connection goes where. So we've got time, alarm, hour, minute and snooze, and a couple of ground connections. Again, we only really needed one ground connection, and we didn't need this pin here, so I could have got away with a 6-pin connector, but it's really not a problem, just to keep it compatible with the other board. Let's have a look at the PCB. So this is what I came up with this time. I thought I'll put the time, the alarm, the hour and the minute all in a line, and I'll put the snooze at the bottom. I was going to go with like a long snooze button, but I've decided not to do that, just to keep things simple. I'm just going to have a regular snooze button at the bottom. The switch probably would just be the same anyway. We have to 3D print the actual button, but I just thought I'd make my life easier. I won't bother with that. I'll just go with standard buttons. Again, we should see those in the next video. Routing on this was pretty simple, because we just had to route one connection on each switch back to our header here. So we've got one here, one there, and one here for the 4 buttons at the top. And then the bottom layer, I've routed the last one here. So I didn't need any vias on this. It's really simple. I did do a ground flood fill on the top and the bottom as normal, mainly just to make the color of the PCB the darker blue when we actually get it manufactured. If you look at the photo view, so yeah, I've decided to go with blue for both of these designs. I could have picked a different color, but I quite like the blue. I think that's my favorite color, and I thought I'll try and keep all of my sort of Arduino / ATmega projects. We'll try and keep all the PCBs in blue, just for some consistency. Now, quickly mention the mounting holes. I wanted to go with just three holes. I was going to put one on each side and then one down the bottom here, but I figured as we're pressing on the buttons, it might make the board flex. The board is very small, so we should get very minimal flexing, but I didn't want to push my luck by not putting a fixing hole in the middle. I don't think we need one between every switch, but I was just worried it might flex slightly if we don't have a good fixing position here. And I figured, I did consider it, but I thought, could I just put 3 across here and not fit one over here? And I thought this button's kind of sticking out on the edge a bit here. I think we need to be sure that the board is secure. So I've gone with the 4th fixing hole at the bottom here. I went with these cutouts initially, just because I thought it would just be more interesting to do a shaped board rather than just a boring rectangle that I always do. But it did actually, when I came to do the 3D modelling of the case, it did actually help me out a bit, because there were some components that were coming into these areas which made me grateful that I had put these cutouts here. I actually designed these PCBs, sent them off for manufacture, and then I started working on the case design. I should really have designed everything up front. I did actually have a bit of a redesign because I did start doing the case design and then realised the power supply circuits just weren't going to work very well, so I had to move things around. But it really is a mistake to go and get your boards manufactured when you haven't done the full design. So I did push my luck a little bit and sent them off for manufacturing early. So then finally we can have a look at the 3D design of this board. I don't think they're the exact model of switches, but they roughly look like that. There's nothing on the other side. Oh, sorry, the connector is on the other side, and that's labelled up, so that should be handy when we come to connect it up. Yeah, that's the switch PCB. So like I said, I have sent them off for manufacturing. They take about 12 days to get delivered, but by the magic of YouTube, we should have them instantly. So here they are in the typical blue JLCPCB box. Just wanted to show you how they come. Not quite sure why. Got a little bit of polystyrene in this one. You don't normally get that. This is how they come vacuum packed. They're pretty difficult to get out of there. This might come out. Yeah, look. Silica gel in there. So this is the switch PCB. We should have 5 of those. So they're quite nice. The other one they've packed slightly differently. Let's get rid of these things. I might have to cut this one out. No, it's going to come out, I think. I think I will cut it. They are really well packaged. There we go, that's the main PCB. So that'll be the front, this will be the back, where all the main components will be mounted. So yeah, that's the 2 PCBs. So what I'll do is I will get them all soldered up for the next video. In the next part, we'll be taking a look at designing a 3D printed case to mount everything inside. So that's it for now. Thanks for watching, and I'll see you in the next one.